So a lot of people have asked about the CAD design of my GNAT cycle cart build. Today I'm going to show you a bit about the 3D CAD modeling that I did for the cart. The program that I use specifically is called Onshape. It's a completely web-based CAD tool, similar in regards to SolidWorks or Fusion 360, but in this case the program is completely web-based, so I can access it really from any computer in the world that has a connection to the internet. There are a few things about the software that are different from SolidWorks. If you're used to CAD packages like that, it takes a little getting used to, but the tutorials are very, very useful. One thing that you do with Onshape that's a little different from other CAD programs is you actually design parts in a they call it a part space, where it's almost like an assembly, but not. So you're designing your parts in this case. So I've got the sheet metal side rails, crossbars, front and rear end plates, suspension, mount uprights, my hoops modeled. Everything is done in these part spaces, and you'll see here a couple different areas. This is how I modeled a lot of the basic parts for the front suspension. I've got steering parts, and a lot of this doesn't really make sense, but use a lot of reference planes, a lot of the drive shaft stuff, components here, modeled up the differential as best I could from creating reference drawings and dimensions from the actual differential. And this is a fairly accurate representation of the differential assembly. So once all these parts are done, you can create sub-assemblies. In this case, this is a sub-assembly of the frame, sub-assembly of the engine. I was fortunate enough to find a 3D model of the Predator engine that is quite accurate to the main machine. In this case, I've got the fuel tank and the exhaust blanked out because I'll be using an external fuel tank and obviously a little different exhaust. Steering shaft, the drag link. Notice that I can move various components around. They're set up with a ball mate. My gas pedal assemblies, steering wheel, disc brake, and then front suspension spindles. So steering spindles, as you see there, and then they all tie back into the main assembly. So this is the main assembly, which is essentially bringing together all of those weldments and sub-assemblies and to create my 3D cart. You'll see that I've got a kind of a human simulant. This is modeled up to reflect the dimensions on my body. I'm about 6'1", so it reflects my leg length, my torso, arms, and in this case, a lot of people have said, "Wow, that cart looks really cramped," but in reality, it's not. As you can see, the legs are fairly stretched out here. You'll see some interference with the pedals. I also have a lot of room to bend my legs up under the steering wheel. So in reality, the cart is quite roomy compared to, or in also easy to get in and out of, as opposed to a lot of the cycle carts that have high wood sides on them, where you kind of have to slide yourself into. In this case, I can step into and out of the cart really without taking off the steering wheel. It's that roomy. So I was pleasantly surprised about that. One of the next things I may do is I may actually lay the steering wheel down a little bit further. I may take it down about 10 degrees or so, just to lay it down more so. It's up pretty high, and it doesn't really match the GNAT cycle cart to begin with. So kind of where I started with the whole design was with the wheels. I purchased up CT90 rims, both the front and rears, and then I modeled those up. And I'll just show you this kind of a section view here of the front wheels. Kind of show you what that assembly looks like. So one of the things I learned on the Cycle Kart forum is a lot of guys are putting two of the bearings, they're like bicycle bottom bracket bearings, putting two of those bearings on the outer race and then the one on the inner race that fits. But as you can see, I've got my spindle here. There's actually a sleeve on the inside between the two inner races, the inside and outside, and then I've got my lock nut on there, and then the rim is pretty accurately modeled as well as I could, and then we modeled the tire as well. And then for the rear, I'll get into this in a little more detail on a different video about my rear wheels, but I did something a little different in the realm of mounting the rear wheels, but I'll show you a little bit here. So I purchased from Azusa, they sell the actual sort of hub components as independent parts, so I purchased the kind of the boss, or I'm not sure what to call it, but the weldment piece that's keyed that attaches to the axle. I purchased that independently, and then through work I burned out a couple of plates. So there's the inner plate that welds to this hub boss, and then I've got the outer plate. And then the outer plate has a small step in it that you can see here where the Azusa axle mounts through. And when I put a nut on the outside, that locks the assembly from sliding out and also from sliding inward. And then I've got these plates I designed such that they pick up the mounting holes, or the 4 holes that I drilled originally in the CT90 hub. Picks those up, so you don't have to drill a different set of holes in the hub. And then the axle, the thing I like is my axle goes all the way through the hub assembly. So I'm supporting my hub completely on the axle. I'm not cantilevering it out with a single mount like most cycle carts use. Turn that section view off. Show you a little bit of the front suspension. So GNAT is interesting in that it's got sort of low side cross members, and then it has these uprights that bolt on top of the side rails that the spring steel springs mount to. In this case, it's a McMaster car spring steel that I got from found out about on the cycle cart boards. And then I was able to source some specialty U-bolts from a company that just makes exclusively U-bolts. Originally I was looking all over McMaster-Carr and Amazon and eBay, and I just couldn't find anything, but then I found this company that made specialty U-bolts, and their prices were pretty affordable. Granted, each U-bolt cost about $15, but in the whole scheme of things, $15 times 2 is cheap. So my whole suspension is modeled very closely after GNAT, with the uprights, the U-bolts, the bolt here. This little tab here was designed specifically for the forming and bending of this sheet metal. Once it was bent up, I cut it off, and the whole assembly was welded together. You'll notice in here that the mounting block is kind of passing through the spring steel. I did that to kind of help sort of do some preload to the suspension. Basically, the way the cart sits in this CAD model, it's completely level, but the way the cart will be designed, it sits a little high. But then with the weight of the engine and everything, that helps settle the whole cart down level. Down on the bottom, I kind of made up my own Hartford, call them shock absorbers. I don't know. Not terribly happy with how they turned out. I've got some bushing material on the inside, and then I also have some space to put some rubber or cork in there to kind of make my own little friction shock absorbers. But this assembly is really nice in that it allows me to adjust this block forwards or backwards, and by doing that, I can adjust the caster angle of the suspension, so I can have my suspension uprights sit more vertical, or I can angle them slightly to give me more caster angle. The suspension is designed with full Ackerman. I also have, if you look from the front view, you'll see I've got like 3 degrees of camber on this, which is very similar to how GNAT is done in reality. My pivots are vertical, and if you draw sort of the imaginary kingpin line down, you'll see that I have a very short or very small, what they call Kingpin Offset. That's from the center of the wheel to the center line distance of the kingpin, where those 2 points meet the ground. The goal is to make that distance as short as possible. We have the small kingpin offset, and what that helps give you is it's almost like a power steering effect. The greater that distance is, or the closer that distance is to 0, the easier it is to turn your wheels, because you're not scrubbing the wheels as much. The whole suspension or the steering works sometimes. Sometimes it misbehaves. You see, I can crank the arm back, and if I crank it too far, everything freaks out. Originally, I designed the steering to have physical stops, where the arm stops in the knuckle, and that worked great, but the problem with that is with the 3-to-1 gearbox, in this large steering wheel, you actually have a lot of torque, and I was finding that I could over torque the gearbox, and there were certain things that were slipping as a result of the excessive torque here and hitting the stop. So what I created was, and I'll hopefully be installing these parts here soon, were some physical stops on the actual steering shaft. So there'll be either set screws or bolt heads that come through here. And basically what they do is they will limit the steering to 135 degrees of motion, which matches the steering limits of the wheels. So this way, when I turn the wheels, they'll hit physical stops here, and as a secondary stop, I'll have the steering knuckle stops. But when you look at the cart from above, it's kind of hard to see here, but I do have full Ackerman geometry where that inside wheel is turning more so than the outside wheel, and that when you kind of have all the alignment of the wheels there. If I draw an imaginary line from the kingpin through my steering knuckle, you'll see that the line essentially intersects at the middle of the rear drive shaft, and that's kind of the goal when you're shooting for kind of a perfect Ackerman setup. That's your target. So we've achieved that there, and it's pretty cool. The one time I took the cart out for a quick test drive, the steering was spot on. It self-centered itself, which was important because my steering gearbox was actually broken a little bit. It worked enough for me to turn the wheels. However, they just kind of automatically came back to straight forward when I let go of the wheel, which was nice. From a drive perspective, a lot of folks have asked about that. I've got my Predator 212 engine in here, coupled with the TAV, and then I've got the 420 sprockets, the 11 tooth coming down to I think it's 18 tooth. Yeah, 18 tooth sprocket, and that's turning what I'm calling a jack shaft. And this jack shaft I made up custom. It's like a two-piece shaft, so it's a main shaft, and then I was able to find a 22 tooth Polaris spline shaft that I cut up and then welded to this shaft assembly. So the jack shaft is turned by the sprocket, and then there is the U-joint assembly turning the drive shaft, which then turns the differential, which is tucked in here. The cool thing about CAD is, say, this part's in the way. You can just make things disappear. So you'll see that I've got the drive shaft, and then I've got another universal joint here running over to the sprocket. And the big thing is whenever you've got this sort of fixed assembly running over to, in this case, the sprocket, you need to have some sort of coupling to allow for misalignment, because there's nothing to say that my initial design is 100% perfect and the shaft would be 100% aligned. So in this case, I put a universal joint here that could pick up the 22 spline output shaft from the Polaris gearbox, and it kicks over to another sort of homemade shaft, two-piece shaft, where it's the standard shaft plus the 22 spline from Polaris, and then I just have a simple it's a 1-inch shaft with a keyway. In this case, this sprocket is a 24 tooth sprocket. Then I have an idler sprocket, and then in this situation here, I've got it's like a 42 tooth But this drive assembly, because my sprocket's external, this is a two-piece sprocket, but I can really easily change my gear ratios. The chain's nice out in the open, and yes, I will be designing a chain guard. I just want to get things going first to figure out what's sort of the optimal chain guard setup. Let's see, a few other things. This center section that mounts the differential, this whole assembly is adjustable. There's slots on it. I designed it so the whole assembly could either move forward or backwards, depending on the optimal configuration for this drive shaft. Because anytime you're sort of designing parts from that exist, and you're trying to sort of reverse engineer them, it's really hard to get them dead nuts on perfect with tape measures and calipers. You're going to be off somewhere. So I planned a little bit of tolerance in there to allow this assembly to shift forward or backwards. And the whole bearing assembly, you can see in there as well, is designed to move as a unit with this cross member assembly. The seat modeled up roughly from the Speedway seat. It fortunately doesn't look like this in real life, but basically I needed to get something that sort of spatially represented the seat as closely as possible. You'll notice I've got my driver set up a little bit because I'm going to have a little seat cushion. The brakes, I was able to find brake calipers that I'm using for the Kart. I was able to find some models of that. So from there I was able to engineer the mounting bracket, the bearings, and a lot of the parts were sourced from McMaster-Carr, and McMaster-Carr is awesome. If you're using CAD, they've got 3D models of virtually everything. So you can pull down the real life models and incorporate them into your assemblies. This is also my brake hub assembly. Let's see, one more thing. Pedals. I kind of created my own pedal assembly. I wasn't really a big fan of the Azusa style pedals, so I kind of made my own. It's a little overkill, but they're cool. There's the master cylinder for the brake. I found basically a spot-on model of that. The brakes work perfect, nice and firm. This is the fuel tank that I'm going to be mounting on the Kart in a little while. There's nice sheet metal brackets. I'm going to make some sheet metal crossbars for the fuel tank to adapt to, and then all this ugly Predator stuff's going to come off, so I'm just hiding some of the items. The exhaust, and the carburetor cleaner, and let's see, that's the gas cap too. So that's kind of what the Kart's going to look like. I have not modeled the skin. That's really hard to do, and it's just not worth my time. So I'm going to basically be kind of fitting that in real life, as opposed to excuse me, modeling it up in CAD. So that's my cycle cart. That is my GN GNAT. Hope you like it. Feel free to leave any questions. Excuse me, been talking a long time. Need to drink some water. About the CAD in the comment section. I'll do my best to answer them. Hope you find it interesting. Again, I use Onshape for CAD, and the software packages. It's all online, and it's pretty affordable for makers. I think there's even a free version, but all your files have to be public. So that's it. I'm going to sign off and go drink some water. Hope you have a great day. Hope you like the video, and subscribe if you want to see more. And we'll see you soon. Cheers.